Natural deduction. In propositional logic, natural deduction was a way to draw conclusions when the truth table method is too cumbersome. At the same time, natural deduction imitates our actual inferences in natural language. When we move to predicate logic, the truth table method is not anymore available. Instead of truth tables, we have to consider arbitrary models. Since models may be infinite and very complicated, there is no mechanical way to go through all models. In fact, validity in predicate logic is a so-called undecidable problem, in the sense that there is no mechanical method to check whether a given sentence is valid or not. For this reason, natural deduction is even more important in predicate logic than it was in propositional logic. What is a natural deduction in predicate logic? Natural deduction in predicate logic is similar to natural deduction in propositional logic. In particular, the rules for connectives are exactly the same. In addition, we have new rules for quantifiers. Rules for the universal quantifier. The elimination and introduction rules for the universal quantifier are: for all elimination rule, from for all xa, conclude a of t/x. The term t has to be free for x in A. For all introduction rule. From A, conclude for all x A. The variable x should not occur free in any uneliminated assumption in the deduction of A. Let us discuss the motivation of these rules. The motivation for the for all elimination rule is the following contemplation. The intuitive meaning of for all xa is that every object in the universe of the model satisfies A when used as a value for x. Therefore, whatever the value of t is, should satisfy A. More exactly, if S satisfies for all xa in M, then for any A in M, S of A/x satisfies A in M. In particular, if A equals the interpretation of T of S in M. By the substitution lemma, S satisfies A of T/x in M. The motivation for the for all introduction rule is the following. We know A, and in a typical situation, X occurs free in A. So A says something about X. However, we have made no assumptions about X because X is not free in any of our assumptions. So X is completely arbitrary, can be anything. Therefore, we are justified in concluding for all x A. More exactly, we have a deduction of A. Intuitively, but this needs a proof, any assignment S that satisfies the assumption of the deduction of A also satisfies A, because this is what deduction means. We should argue that any assignment that satisfies the assumptions of the deduction of A also satisfies for all xa. To this end, suppose M is a model and S satisfies all the assumptions of the deduction of A. Then for all A in M, also S of A/x satisfies those assumptions, since X is not free in them. This needs a simple proof, but we omit it. Hence, S satisfies for all xa. Example of deduction. Let us look at the following natural language inference. If every millionaire is happy or not busy, then every busy millionaire is happy. The reason why we think that this is a valid argument is the following. Take X and assume it is a busy millionaire. By assumption X is happy or not busy, but we assumed X is busy, so X must be happy. In the language of predicate logic, this is if for all x, left parenthesis, p0 of x implies left parenthesis p1 of x or not p2 of x, right parenthesis, 3 times, then for all x, left parenthesis, p0 of x and p2 of x, right parenthesis, implies p1 of x, right parenthesis. We can argue informally in predicate logic as follows. Take x and assume p0 of x and p2 of x. We try to derive p1 of x. By assumption, p0 of x implies, left parenthesis, p1 of x or not p2 of x, right parenthesis. From this and p0 of x, we get p1 of x or not p2 of x. The assumption is p2 of x, so p1 of x. Since x was arbitrary, we get for all x, p0 of x implies, left parenthesis, p1 of x or not p2 of x, right parenthesis. With this in mind, we can actually build a real natural deduction.
Let us build the deduction. Our assumption is for all x, left parenthesis p0x implies left parenthesis p1x or not p2x, right parenthesis. And we try to deduce the formula for all x, left parenthesis p0x and p2x, right parenthesis, implies p1x, right parenthesis. We will probably end this deduction with an introduction of the universal quantifier for all x. So let's concentrate on finding a deduction for the implication. So we make a temporary assumption p0x and p2x. And we try to deduce p1x. When we compare this temporary assumption p0x and p2x with our assumption for all x, p0x implies p1x or not p2x, we can immediately see that if we eliminate the universal quantifier for all x from the assumption, we get p0x implies left parenthesis p1x or not p2x, right parenthesis, and from the temporary assumption p0x and p2x we can get both p0x and p2x. So now it's just propositional logic from this on. First we use implication elimination to p0x and the implication p0x implies left parenthesis p1x or not p2x, right parenthesis, and we get the disjunction p1x or not p2x. So let's compare this with the conclusion p2x on the right. Clearly we can somehow get p1x from this. Okay, but how? Okay, p1x or not p2x is a disjunction, so we should try to use disjunction elimination. So we set up the stage for an application of disjunction elimination. This means that we write as a temporary assumption the first disjunct p1x, which by the way happens to be what we want to conclude anyway, and the other temporary assumption not p2x. From both temporary assumptions separately, we should be able to deduce p1x. From the first temporary assumption, which is p1x, it's trivial because this is p1x, so there is nothing to do. But we have to start from not p2x on the far right and somehow deduce p1x. But we know p2x. When we set this together with not p2x, we get a contradiction. And then when we introduce negation, we get not p1x. And from that, by negation elimination, p1x. So now one application of the disjunction elimination rule gives us p1x. And implication introduction gives us left parenthesis p0x and p2x, right parenthesis implies p1x. And finally, introduction of the universal quantifier we get for all x, left parenthesis p0x and p2x, right parenthesis implies p1x. We have to now check that when we introduce the universal quantifier, the variable x is not free in any uneliminated assumption. But the only uneliminated assumption that we have made is the very assumption in the beginning, which is for all x, and then something. So this is a sentence which starts with the universal quantifier for all x, so certainly x is not free there. So this application of the universal quantifier introduction rule is permissible. And the deduction is ready.